Okay, so in this problem we have a particle of mass m, which moves along the smooth path shown. In this problem we're asked to determine the speed v0 such that the particle loses contact with the semicircular hill at a given value of theta, and to also use the result to determine the normal contact force acting on the block at a different value of theta. So to work through this problem, I'm going to start by defining a coordinate system along the part of the hill here that we're interested in. And so I'll call this the E sub n and this the E sub t directions. In other words, I'll use conventional path coordinates. If I sketch a free body diagram of this particle, somewhere along the hill, I know I'm going to have a normal force acting outward, which will be oriented here at an angle theta, and I'll have the force due to weight acting down, which will be oriented here like so at an angle theta as well. In addition to this, I know that this is going to have an acceleration that's mv squared over r in this case, in the E sub n direction, and m times v dot in the E sub t. So if I go ahead and work through this problem by first of all summing forces in the t direction, I'm going to have that's going to equal mv dot, and this is going to give me here that the weight, mg times the sine of the angle theta, is going to equal m times v dot. In addition to that, and I can call that equation 1 by the way, and in addition to that I can sum forces in the n direction and set that equal to m times v squared over r, and this is going to give me in this case that n, it's going to give me that mg times the cosine of the angle theta minus n is equal to m times v squared divided by r, and we can call this equation 2. Now in this particular problem, at least in part A, we're asked to find the critical speed for which of v0 for which this thing loses contact. And so the way I'm going to do that is I'm going to take equation 2 and I'm going to set n equal to 0 because we know that's going to occur when we lose contact. And this is going to give me the result that g times the cosine of the angle theta is equal to v squared divided by r. If I solve that, that tells me that the critical speed at which I'll lose contact, which I'll call v critical, is going to equal the square root of g times r times the cosine of what I'll call theta critical, the angle we're given in the problem. Now I want you to keep in mind that this does not tell me the speed I want to have at the top, v0, because in this case, from equation 1, we know that v dot is changing at the rate of g times the sine of the angle theta. So to figure out what I need for v0, I want you to think of this a bit like a picture. What we have here is that at the top of the hill, at theta is equal to 0, I have a speed here v is equal to v0. At some later point here, where now theta is equal to the theta critical value we're given, I want to have the speed of v is equal to v crit. To help us doing that, I'm going to start by noting that v dot can be expressed as dv dt, and that's going to equal g times the sine of the angle theta. And I can expand this a bit on the right hand side because I want to introduce the angle theta, so I could rewrite this as dv d theta dt. But I don't want any time dependence in here, so I'm going to try to express this yet a different way. And the way I'm going to do this is to note that the left hand side I can expand even further and write this as dv d theta dt, d theta ds times ds dt, and that has to equal g times the sine of the angle theta. Now why did I do this? Well, let me clean up the right hand side here a little bit. I can rewrite this as dv d theta. D theta ds can be determined because we know that in this case s, the arc length, is going to equal r theta, which means that ds is going to equal r d theta. This of course means that d theta ds is going to equal 1 over r. So this is going to give me times 1 over r, and then ds dt is simply going to be v, and that's going to equal g times the sine of the angle theta. If I multiply through by the differential element d theta, this is going to give me that 1 over r times v dv is equal to g times the sine of theta d theta. I can then integrate this on both sides, and note that I'm going to start. Let me add a little buffer space here. I'm going to start from a speed of v0 and move to v critical, and then here I'm going to start from an angle 0 and move to theta critical. This is going to leave me with 1 over r times quantity v critical squared minus v0 squared divided by 2 is going to equal minus g times the cosine of the angle theta, evaluated at theta critical and 0. If I work this out, I can find the numerical value for V0 needed to leave the track at the instant total. This will give me the answer to the first part of the problem. For the second part, I'm going to come all the way back up here and use equation 2 again, and say now that I've found V0, if I want to determine the speed for which I'll have at a given value of theta, I can solve for equation 2 and find the normal force at that instant. And I think at that juncture, using the results I have here given in the problem statement, it becomes a purely numerical endeavor, one that I know you can handle. I'll leave it up to you to wrap it up. I know you got it. Best of luck.